Intermittent fasting, once viewed as a mere weight loss strategy, is now being explored as a powerful tool for resetting the brain's sugar metabolism and enhancing long-term neurological resilience. At its core, intermittent fasting involves alternating periods of food intake with periods of calorie abstinence, ranging from hours to entire days. While it dramatically shifts systemic energy balance, it also initiates a series of finely tuned molecular responses within the brain. Among these, improved glycogen regulation, enhanced insulin sensitivity, and activation of autophagy stand out as key mechanisms that may reverse early signs of neurodegeneration and restore impaired energy metabolism. Under normal fed conditions, the brain relies heavily on glucose, delivered continuously through the bloodstream. In this state, astrocytes, the brain's primary glycogen reservoirs, store and regulate small amounts of glycogen to buffer short-term energy needs. However, in individuals with insulin resistance or chronically high blood sugar levels, brain glucose handling becomes impaired. Neurons, already energy-intensive, struggle to maintain stable ADP production, and astrocytic glycogen cycling becomes dysfunctional. Over time, this metabolic rigidity can lead to oxidative stress, mitochondrial dysfunction, and impaired synaptic signaling, all of which are associated with cognitive decline and the early stages of diseases like Alzheimer's. Intermittent fasting interrupts this pathological cycle. By temporarily withholding glucose from the bloodstream, fasting forces the body and brain to adapt by tapping into alternative fuel sources. Glycogen stores in the liver and astrocytes are gradually depleted, prompting a shift in energy metabolism toward fatty acid oxidation and ketone production. This metabolic switch is not merely a backup system. It introduces a cleaner, more efficient fuel, ketone bodies like beta-hydroxybutyrate, that generate less oxidative stress and offer neuroprotective effects. In the brain, ketones have been shown to enhance mitochondrial function, reduce inflammation, and support BDNF, brain-derived neurotrophic factor, signaling, which is crucial for plasticity and memory. But intermittent fasting does more than just provide a cleaner energy source. It activates cellular stress response pathways that promote repair and detoxification. Chief among these is autophagy, a process in which cells break down damaged components, misfolded proteins, and dysfunctional mitochondria. In the brain, impaired autophagy is linked to the accumulation of beta-amyloid and tau proteins, key markers of Alzheimer's disease. Fasting-induced autophagy may help clear these toxic aggregates before they become entrenched, effectively slowing or reversing early neurodegenerative processes. Another critical benefit of fasting is the potential to normalize astrocyte neuron metabolic interactions. During periods of caloric restriction, astrocytes engage in more active glycogen turnover, which not only improves their energy flexibility, but also helps reestablish proper lactate shuttling to neurons. This metabolic communication is vital during high-demand periods, such as learning or recovery from stress. A fasting-enhanced astrocyte can better modulate glucose availability, regulate neurotransmitter cycling, and support overall synaptic health. Evidence from animal studies and early human trials supports these benefits. Rodents subjected to intermittent fasting regimes show improved memory, reduced inflammation in the hippocampus, and a decline in age-related cognitive impairments. Brain imaging in fasting humans reveals enhanced insulin sensitivity, increased ketone uptake, and improved connectivity in memory-related regions. While long-term data in humans is still limited, the preliminary results are promising and suggest that even modest fasting windows, such as 16:8 or alternate day fasting, can confer meaningful neurological benefits. Yet caution is necessary. Not all brains respond the same way to fasting. In individuals with underlying metabolic instability, hormonal imbalances, or eating disorders, fasting may exacerbate stress, reduce sleep quality, or impair cognitive performance. The timing and intensity of fasting must be tailored, especially for older adults or those with pre-existing cognitive decline. Moreover, fasting alone is not a cure. It must be paired with a nutrient-rich diet, adequate sleep, and physical activity to yield its full cognitive advantages. Still, the idea that intermittent fasting can reset brain sugar metabolism is no longer speculative. It offers a powerful metabolic reset that can recalibrate glycogen storage, enhance mitochondrial efficiency, and engage the brain's own repair systems. In a world of constant caloric overload, insulin resistance, and circadian disruption, fasting may offer a much-needed break, one that gives the brain space to clean house, rebalance its energy, and preserve function well into old age. As science continues to unravel the complex ties between metabolism and cognition, intermittent fasting stands out as one of the most accessible and biologically grounded tools for protecting the brain.